Good afternoon, class. So yesterday we already discussed about the terms associated with refraction of light. Okay, so as I told you yesterday, this diagram is very important. Okay, I already made you understand about how it went, how it goes through, how the normal, the point of incidence, everything, right? Air, which is a rarer medium, it enters into the glass slab, which is denser, and then it goes again to the air again, which is a rarer medium, right? You remember this diagram by heart. Okay, so I hope so you're all well versed regarding all these points, right? And what is more important here is emergent ray and angle of emergence, since they are new terms, right, in this refraction. Okay, you check these. Okay, these points also is very important. All right. Okay, so next now we will go to lateral displacement. So what is lateral displacement? Okay, so before going to what is lateral displacement, I would like to first come again in this diagram. All right, so here, do you see this incident ray PO, right? This incident ray, the ray which is coming is always the incident ray, and that is known as, that is PO. Okay, so this PO, if it was only in air, if it didn't enter the glass, it should have went in the straight line. Okay, that is OT, right? Should have went in the straight line, but instead, when it hit this, it changed its path, right? And it gets shifted. Right, the incident ray gets shifted. Okay, so here the incident ray PO, which should have continued along a straight line path OT, gets displaced. Displaced means gets changed, all right, along O-S due to the refraction. Why does this happen? Because of refraction of light, right? Because according to refraction of light, when an incident ray enters from a rarer medium to a denser medium, the path gets displaced. Okay, therefore there is a lateral shift on the incident ray. Do you see? There's a shift on emerging. Okay, you see this on emerging? It should have emerged in this way only, right? It should have emerged in this way, but now it is emerging in this way. All right, there is a lateral shift, okay, which is represented by O-L. Okay, you see? Oh, wait. There is a lateral shift on the incident ray on emerging. The glass slab is represented by the perpendicular distance. Do you see there is a perpendicular distance drawn now? From here, this is the real line, okay, that is incidented. This is the fake one, which you just drew with dotted lines. So what is the difference between these two? It is this, O-L. Now the difference between these two, right, this perpendicular which is drawn here, do you see it is a perpendicular? How is it a perpendicular? Here it is 90 degree, here it is 90 degree. If you see it in this way, right, if you see it in this way, there is a 90 degree here. You see that? Or if you see it in this way, okay, do you see this? And there is 90 degree because there is a line here, right? So 90 degrees. So what? Perpendicular. We call it a what? A perpendicular. All right. So this perpendicular O-L, okay, which emerges out, is known as the lateral displacement. So definition: the perpendicular shift in the path of the incident ray while emerging out of a rectangular glass slab is called the lateral displacement. So I already explained it to you, right? So that is the definition. Okay, now there are three conditions here. What happens? It increases with increase in the angle of incidence. If there is an increase in the lateral displacement, there is also an increase in the angle of incidence. That is, they are directly proportional. Okay, directly proportional. Right. This term means if the lateral displacement increase, the angle of incidence also increase, and if the lateral displacement will decrease, even the angle of incidence also will decrease. Okay, so you have to remember these 3 points. The lateral displacement increases with increase in angle of incidence. The lateral displacement increases with thickness of the slab. Okay, suppose if the glass is small like this, the lateral displacement will also be small. Suppose the thickness is 2 meters. Therefore, the lateral displacement will also be 2. Okay, like it will just be small. Okay, and if the glass thickness is this much, then even the lateral displacement also will be increasing. All right. Then lateral displacement and optical density of the slab also increases with increase in each other. Okay. So that is for lateral displacement. So what is important in lateral displacement? The definition, you refer to the diagram and these 3 points. All right. Now we will move on to the next, that is the laws of refraction. Okay. So the laws of refraction. This is very, very important. Laws of reflection also is very important. Laws of refraction also is very important. Okay. So according to the law of refraction, what does it state? These I cannot help you. You have to by heart these. Okay. So what does it state? The incident ray. You already know what is the incident ray, right? The incident ray, the refracted ray, not the reflected ray here. The refracted ray and the normal. Okay, it is similar, somewhat similar to reflection of light, right? But here, this point is important. The incident ray, the refracted ray, and the normal to the surface of separation of two medium at the point of incidence. To the surface of separation of two medium. Because here, there are two mediums now, right? In refraction, there are always two mediums or more, right? There's not only one medium. Okay, there are two mediums or more. So the incident ray, the refracted ray, and the normal to the surface of separation of two media at the point of incidence all lie in the same plane. They are all in the same plane. All right. Then this one is very, very important. This is a very, very important point. Let me tell you why. All right. So here the ratio. When they say ratio, you know, right? It is always A by B. Right? It is always in the form A by B or A is to B. Right? That is ratio. So the ratio of sine of angle of incidence, sine of angle of incidence to the sine of angle of refraction is constant. What do you mean by constant? It is always the same. Okay? That I will tell you during verification. So it is always constant, it is always the same. Alright? It doesn't change. Okay? Even if the angle changes, okay, the sine I by sine R will always remain a constant. So here, the ratio of sine of angle of incidence to the sine of angle of refraction is constant. That is, sine I divided by sine R is equal to how much? Is equal to constant. Now this, I already told you this is why is it very important? Because this is also known as the Snell's law. Now in the exams, if they tell you state the Snell's law or state the laws of refraction, right? If they ask you to state the laws of refraction, you'll state these two. But if they ask you to state the Snell's law, you'll state the second one. Along with this, I want you to keep this. That is sine I by sine R is equal to constant. First, you write the ratio of sine of angle of incidence to the sine of angle of refraction is constant. Alright? Then you give this. Okay? Then you write, this is known as the Snell's law. Then, Snell's law was stated by Willibord, okay, Snell, okay, his name was Willibord Snell in 1621, all right. So this is the laws of refraction, okay. Remember this one, very, very important, okay. Then verification of the laws of reflection. Now, how do you verify the law of refraction? Okay, that one you go through on your own, but I'll just give you a gist of what it means, okay. Now, suppose I have a prism, okay, a prism which is a glass. All right, we did this during our school days. Okay, so we put the prism, we put from different angles. So I'll just tell you small things. Okay, I don't want to go into the depth of this. Okay, you'll be doing in 11, 12 if you want. Okay, so you put the prism. After putting the prism, you check the prism from different angles. That is 30 degree, 35 degree, 40 degree, 45 degree, and 50 degree. There, from all the angles, you check the table 3. Okay, I'm talking about table 3. You check all the angles, okay, from different angles. The angle of incidence that is coming is from 30 degree, okay. After coming from 30 degree, you will see another reflected angle, okay, that you have to measure. Then here in the first case, you got 19.5, right? In the second case, which is 35 degree, see, there is a prism, right? Here you will check from this angle first, okay. You check, you see from your eyes, from this angle. Okay, you put the incident from here. Then it gets reflected from here. You measure this one. When after measuring this one, you get 19.5 degree. Right? Then you put at 35 degrees. Okay? Then it gets reflected again. This reflection is 22.5 degrees and so on. Okay, with 30, 35, 40, 45. Okay, and so on. Right? After getting the angle of incidence and the angle of reflection, you can get the sine I, because sine is perpendicular by base. Right? So you calculate how much is the sine. After calculating the sine, you also sine I, you calculate the sine R, right? This is where it gets, okay. See, after calculating for sine I, then you calculate for sine R. After calculating sine I and sine R, what do you do in the next step? You divide these two, sine I by sine R, right? So See, do you see the values there? How much? In 30 degree, you got 1.51. In 35 degree, 1.5. 40 degree, 1.49. 45 degree, 1.5 again. 50 degree, 1.5 again. What does this tell you? What does this tell you? This tells you that sine I and sine R is always almost the same, that is 1.5. You see, most of the values are 1.5 there, right? So 1.5. That is, even if it is 30 degree, 35 degree, 40 degree, 45 degree, 50 degree, okay, all these degrees will always give you 1.5. That is why sine I by sine R is equal to constant. You see, constant means the same, that is 1.5. You understand? That is the verification. I just gave you just please read on your own. Okay, please read nicely. I just gave you the gist of this, how it goes. Okay, you read that on your own. Alright, so I hope so you understood about that. Okay, so next we will move on to refractive index. Okay, so refractive index is nothing but the ratio between sine I or sine of angle of incidence of one optical medium. Okay, this is important. It is also the ratio of sine I but of one optical medium to the ratio of sine R of another optical medium. You see, this is of one medium to another medium. Sine I of one medium divided by sine R of another medium. Alright, here we can also denote refractive index with n. Alright, so if I write n here, 1, 2 is equal to sine I by sine R, you will know that this is refractive index. Why? Because they are of two medium. This is the first medium and this is the second medium. You understand? So refractive index is the ratio of sine of angle of incidence of one optical medium to the sine of angle of reflection of another optical medium. Okay? See, this is the example. If angle of incidence is formed in air, right? Like for example, that glass slab which I just drew, the angle of incidence there was in air. And the angle of reflection was in glass. So what do you write? N, air, glass. Right? Air and glass. Because angle of incidence was at what? Air. And angle of reflection was at what? Glass. Right? So N, air, glass is equal to sine I by sine R. Understand? Okay. This you should remember. Okay. If it is formed in water and glass, then it should be NWG is equal to sine I by sine R. Okay, these are simple terms. All right, so this definition very important for refractive index, and even this, okay, this representation. All right, so next we will talk about the refractive index and the speed of light. Okay, so we already discussed in the earlier classes what is the speed of light. The speed of light is always 3 into 10 to the power 8 meter per second. This is very, very important. Okay, the speed of light is 3 into 10 to the power 8 meter per second. But this is in vacuum. Okay, that is in space. Alright, space in vacuum. In vacuum, it is this much. Okay, so refractive index of a given optical medium is the ratio between the speed of light in vacuum. Okay, refractive index of a given optical medium. If they're asking you here, see, this is refractive index. It is of one optical medium to another optical medium. Here they're giving you of speed of light, right? So it is the ratio of a given optical medium. Okay, so the ratio of a given optical medium. Here the given optical medium is speed of light, right? So it is the ratio between the speed of light in vacuum divided by the speed of light in a given optical medium. You understand? It is the speed of light in vacuum, that is in nothing, and the speed of light in given optical medium. Okay, that is if it is glass, water, air. You understand? In a given optical medium. It can be any optical medium. Alright, so it is denoted by N is equal to C by V. Remember this one also very important. If it asks you if they ask you about the refractive index of speed of light, it will be speed of light in vacuum by speed of light in a given optical medium. Now this is also very important. Suppose there are two terms, P and Q. If it is written N, P, Q, this P is first. So it will be speed of light in P divided by speed of light in Q. Alright? Do you see this? P and Q. Right? However, N, P, Q, then P will be up, this Q will be down. Right? However, if it is NQP, QP, then this Q will be speed of light in Q divided by speed of light in P. This is very important. Okay. NPQ means speed of light in P. Don't write SOL, okay? I'm just writing, there's no space. You write speed of light. This is speed of light in Q. Alright. If it is NQP, then it is speed of light in Q divided by speed of light in P. This is refractive index of the speed of light. Okay. Here in your book, they will also discuss about the speed of light in wavelengths. So if that is the case, then the refractive index will be wavelength of light in vacuum divided by wavelength of light in optical medium. Alright, which is denoted by, wavelength is always denoted by lambda. Right, so it will be N is equal to lambda C divided by lambda V from here. Okay, for speed of light is C by V only. For wavelength it will be wavelength of light in vacuum and wavelength of light in optical medium. Alright, so I will stop my class here. Next week we'll discuss about optical density, rarer denser medium, and some numerical problems. Alright, so yeah, we have a lot. Okay, so thank you class.